in the upper right-hand corner, you see the water molecules connected up there. That is a hydrogen. Okay, and then we talked about how kind of the next thing that looks like a kind of a circle there is the water molecules all stuck together in their solid state. We have a lot of water bonding, a lot of hydrogen bonding, and then the next one is kind of, it's got some hydrogen bonding, so that's a liquid. And then absolute humidity is the top one, and mixing ratio is the bottom one. So absolute humidity depends upon volume, and mixing ratio does not depend upon volume. And when we got started talking about humidity, we kind of stuck with mixing ratio, because when we talk about saturation amounts, that's in terms of mixing ratio. For the next one, I kind of brought in, I don't know if you recognize this little figure right here. This is like kind of the third of three, kind of we talked about not saturated. But when the air is saturated, the thing is that there's the same number of evaporating molecules as there is condensing. So the rate of evaporation is equal to condensation. And kind of related to that is this idea of saturation mixing ratio and equilibrium vapor pressure. Well, so right here, I know this is hard for you to read this table, but the two columns, the first column is temperature, and that second column is that one that you guys use to remember to come out, calculate relative humidity. That's the saturation amounts. Trend of saturation in, relative humidity. What is relative humidity? Well, what you do is you take the actual amount of water vapor, you measure that, and you divide by the water vapor required for saturation. You get that from the table. Trend in mixing ratio with temperature. That's the old adage that warm air holds more water vapor. Okay, and actually you can see that from the table, because as you go down in temperatures, remember that's the left column. As you get the temperatures get warmer, actually the saturation mixing ratio gets bigger. The next one, dew point temperature. That's the temperature to reach 100% relative humidity, dew point temperature. And then humidity throughout the day, I brought in a figure again. And by the way, this document I'm going to push out there under Twitter as a PDF, so actually you can print these too. So this one actually is what humidity does throughout the day. Remember, you have the highest relative humidity about 6 a.m., and you have the lowest relative humidity about 4 p.m. That's assuming that there's no extra water vapor added. And then a hygrometer measures humidity, and a sling psychrometer also measures humidity, and you guys did that in this room, where basically you had two thermometers. This one without the white thing, that's your dry bulb, and then you had a sock there that you wetted, and you slung it around. We talked a lot about adiabatic cooling, but I have what is an adiabatic or a diabatic process. So a diabatic process is here in purple, when basically heat is exchanged with the environment. Adiabatic is no heat is exchanged with the environment. So adiabatic cooling is where basically a chunk of air rises, expands, and it just cools in and of itself. And then the lifting condensation level, LCL, that's the elevation to which air lifts and cools to the dew point temperature. So actually, lifting condensation level and dew point temperature, I kind of have them all there. And then we're to the environmental lapse rate, or the ELR. Remember, that is the, you send up a weather balloon for the ELR. So the ELR, environmental lapse rate, is the temperature of the atmosphere with increasing elevation. You would think that temperatures get cooler as you go up in the troposphere, and they're supposed to, but remember we have those temperature inversions. So the dry adiabatic rate, or the DAR, I went ahead and brought in a figure here. Okay, this actually this bottom part, if you just kind of look at, remember we said if you don't see cloud, that actually that chunk of air is in these figures expanding and cooling at the dry adiabatic rate. The dry adiabatic rate is about 10 degrees Celsius per kilometer. And the reason it cools as it rises is it expands, it rises, it expands, and it cools. So the wet adiabatic rate and how it's different than the dry adiabatic rate, your chunk of air is still rising and cooling, but we have condensation going on. So you have a condensing chunk of air that's rising and cooling, but in blue here I said the difference here is that you have the latent heat of condensation, C-O-N-D for condensation, and that slows your cooling. And remember this, I put it in green here. I'm like, grr, okay, your author actually first uses a wet adiabatic rate of 5, and then he uses a wet adiabatic rate of 6. Okay, so I think you'll be fine with either one. The next one, the lifting mechanisms, remember they look like, where'd they go? Here they go, over here in orange. The lifting mechanisms, we had orographic lifting, frontal wedging, convergence, and localized convective lifting. So those are the 4 lifting mechanisms, so kind of know what they do. And then last but not least, the 3 types of stability. We have absolute stability, absolutely unstable, and conditionally stable. And if you go back to what your weather balloon says, if your ELR is less than your wet adiabatic rate, it's absolutely stable. If your ELR is greater than your dry adiabatic rate, DAR, then it's absolutely unstable. And if your ELR is in between your WAR and your DAR, and you have some moisture, it's conditionally stable. So that's a lot in Chapter 4. Chapter 5 looks like this. Cloud condensation nuclei, that's the dirt, the thing that gets condensation to get started in the first place. We have 2 versions of condensation nuclei. We have the water-loving, which are hygroscopic, and the water-fearing, which are hydrophobic. You're almost like, why would you put in for the job if you're afraid of water? To connect water particles. And then how are clouds generally classified? It's called, you know, I've been talking about flat and fluffy. Okay, that's one way to classify clouds. Remember, flat is stratus, fluffy is cumulus. That's sometimes called form or appearance. Another way is elevation. We have low, middle, and high. And the third way is precipitating. I don't know if that really looks like precipitating. Precip. I think I'm missing a C. Something like that. And if it's precipitating, we go with nim or something in the name. Middle clouds are alto, high clouds are cirrus. So that's kind of the 3 things, how you classify them. And then I went ahead and brought in this little figure for the 10 cloud types. So just generally know the 10 cloud types and kind of what they're like. Like alto stratus would be middle flat. Okay, cirrus is the highest flat and that sort of thing. Lenticular clouds, those are associated with mountains and they look like UFOs, lenticular clouds. And then the 4 types of precipitation, went ahead and brought in kind of the figures. The first 2, you can actually kind of see how that first one, it starts out in the blue, it's snow, and actually it just melts, and so that gives us rain. The next one, it's blue all the way down, so that gives us snow. The other 2 actually have what we call temperature inversions in place. So the pink part is where it melts, and then the first one, like the third one over, it has time to refreeze and pelletalize, so that will give us sleet. And then the next one will give us freezing rain. All right, so fog looks like this. 4 different types of fog. We have radiation, advection, upslope, and the evaporation fog is the last one. So kind of know your fogs and how they form. Supercooled water is just water that is liquid at temperatures colder than or less than 32 degrees Fahrenheit. liquid water droplets versus ice crystals in a super cooled cloud. So I brought in this of 3 figures. So this figure right here with the kind of Mickey Mouse looking water vapors, and of course the blue orbs are super cooled liquid water, and you see that beautiful little snowflake. So the thing is that the snowflake actually is going to get bigger because it's actually extra saturated. It's what we call supersaturated, and that's what kind of the 105% supersaturation is kind of showing you. Then we talked about warm clouds. Warm clouds don't have anything to do with snowflakes, but warm clouds, the water droplets grow by what we call collision and coalescence. So this down here at the bottom, I forgot my right here. This is the collision coalescence process, where basically you have a collector droplet that's running into the little ones and gobbling them up. That's how warm clouds create their precipitation. Hail from CB stands for, CB is the abbreviation for cumulonimbus cloud. So hail, what I'm hoping you'll know is that hail does not fall from that up there. That up there is basically snow, and then it either makes it a snow or melts and becomes rain. Hail actually comes from storm clouds, cumulonimbus clouds. We'll be talking more about hail. The next one, cloud seeding. There's actually, you can use carbon dioxide too, but I think on your test it says silver iodide. Basically you spray that in the air as kind of fake cloud condensation nuclei, CCN. And the last 2 terms, I think you had a homework question about this. Virga and fall streaks, what they have in common is their precipitation that's falling into dry air. And it doesn't really make it as precipitation because it dries, it evaporates before it reaches the ground. Precipitation evaporates into dry air before hitting the ground. And there's the couple of pictures that go along with those. So that was a good chapter too. And so chapter 16 is not as much. So the first term says white light from the sun. So I don't think I emphasized it in lecture, but the sun is sending all sorts of different radiations, and when it sends this light, it's the Roy G. Biv light, okay? And so that's all I mean by white light coming from the sun. Reflection and law of reflection looked kind of like this, where basically we call the angle of reflection, the light that's going to leave, is equal to the angle of incidence, the light that's coming. That's the law of reflection. Refraction, we talked a little bit about that in chapter 16. We have the refraction that kind of bends the light in its entirety, and then we have the refraction that actually separates light into its components. Both of them occur bending light because light is moving into a different medium. So as it leaves one medium and enters another one, refraction occurs. So there's a picture from your textbook where it's going from air into water and it's being bent. It's refracting. Internal reflection. I got to bring in this adorable picture. Okay. So internal reflection happens in rain droplets, and internal reflection can actually happen just as light bounces. I kind of drew an arrows bouncing from that gal up to the interface, okay, back down, and actually kind of back in all directions, including the direction of the camera. So it looks like she has kind of a mirror up there where the water hits the air. I think that is so cool. Earth's atmosphere, refracting light. And so I brought in, actually it's a test question kind of along the lines of what this was about. Remember we said that the sun is really low, but it looks like it's higher. And the sun's light is being bent because of the different densities, like the thin air. Light travels at a different speed than thicker air. So I think it would travel faster at the thinner and slower at the thicker. Then the next one, mirages. We talked about a superior mirage, which floats, and an inferior mirage, which is below the horizon. But what they both have in common is they happen because of differences in temperatures. So there's an inferior mirage right there at the top and a superior mirage in the bottom. So also an inferior mirage is upside down and a superior mirage is supposedly right side up and floating. But I swear that one that I got from the internet looks like it's inverted. Then the last one, okay, I just went ahead and brought in this table from your textbook that lists the third column is the different optical things that, mirage, halos, sundogs, sun pillars, rainbows, coronas, iridescent clouds, blue skies, and red sunsets. And then the last column is what's causing them. So I think that's kind of cool. And then I went ahead and added one line, like I told you guys, the needed conditions for rainbows. I just went ahead and drew that little picture again. You know, you need to have the sun at your back. It has to be clear, like my slides said, or your textbook says, it has to be clear between the sun that's low on the horizon and your liquid rain droplets. And in the liquid rain droplets, you're going to see that creation we call a rainbow. Just beautiful. Okay, so